All right. So these chapters that you see here might not line up with your like mathematic chapters, right? They're just I pulled different chapters from when I did on-ramps and stats and just different topics in general. So don't focus so much on the chapters, but more on the topic. And we'll start sort of in the beginning a little bit. We want to definitely be able to differentiate between the types of variables that we're working with, right? Whether that's numerical versus categorical. Yeah, because depending on the type of variable that you're dealing with is how you represent the graphs or the charts or tables or histograms and then what kind of test you're going to do, right? If you're going to do a chi-square test versus a z or t test, or all the different tests are based on which type of variable you're working with. So the foundation is important, right? Numerical meaning quantitative, right? It's another word that they use. Quantitative. And then categorical would be qualitative. Variables. But numerical and categorical are the most common ones, right? The way they express it. Basically, anything you can find the average of would be numerical, right? Sometimes you can represent categories in numbers, but you can't find the average of like how many males do we have? You don't say like there's 17 on average, right? Like when you're dealing with males versus females, you're dealing with colors or things like that. Those are categories. You use a number to represent how many are in that category, but you don't take the average, right? You don't find the average number of browns versus yellows and stuff like that, right? So if you can find the average of something, you're dealing with numerical. If you can't, right, you're dealing with categories. So colors, gender, grade levels, right, like sophomores. Because you can't really find the average grade level. You can find a number, but it won't make any sense. And then from here, we want to represent the data in certain ways, right? When we're dealing with numerical, we're dealing with like box plots or histograms. You can also do dot plots, right? I'm just going to go over some stuff before we jump into the notes that I made. But these are like the general ways of looking at numerical data. Most commonly, you're going to be focused on these two right here, right? A histogram, the 5-number summary. We'll talk about that in a minute. Histograms, how to read it with left skewed, right skewed, right? That kind of stuff. And then for categories, then we're dealing with two-way tables, which is something like maybe you're comparing males and females and what kind of phone they have, like an iPhone versus like a Samsung, right? This is a two-way table because you can read data in two different directions, right? And you'll get more into that for like chi-square and the next chapter you're going to get into. But like a two-way table is a very common way to look at categories, right? How many males have a Samsung versus how many females have an iPhone, and you can compare those numbers and find the proportions and stuff like that. Pie charts, and then bar graphs, right? With the biggest difference between bar graphs and histograms is they look similar because they both have bars, but histograms is continuous, right? You have data that is continuous versus bar graphs, because they're categories, they're separated. They can't be touching, right? There's no, technically, and at least in the categorical range, when you're dealing with colors, there's no like in between, right? It's like red, blue, green. Although you can have like a spectrum and you can know without getting into specifics. But when you're dealing with heights, right, which is like a numerical value, the heights you can find in between 5 feet and 6 feet. You can find between 4 feet and 4.5 inches, right? You can find in between, which is why it's more, the graphs are like stuck together. And there's different ways of describing those two, right, depending on the variable. And we'll get into some of those descriptions and stuff. this one is organized, right, from like least to greatest. There's no way to organize this from least to greatest. You can't do blue goes first and then purple and then like there's no order in that. So you can't really describe like, oh, there's a trend here. You can't really describe trends here as you can here with like means and standard deviations and such. Right? The trends would be more like, well, there's more of this number than this number, but you can't really say that there's, as the color increases, the numbers decrease, right? That doesn't really make sense because there's no order in this scenario. So, no order. Okay, so this is sort of like the beginning, right? Can you tell the difference between numerical, categorical? How do you represent the data? Can you find the averages, means, standard deviations? And then you start getting into some of the actual math. Yeah, and if you have questions at any moment, just let me know. Okay. So then here you have a scenario, right? We're given a list of numbers. The goal here is to organize them from least to greatest. We're not going to do the math, but we're going to talk about how to go about it, right? You would write them from least to greatest. And then you can start finding your 5-number summary, right? When you're given data, we're going to want to then figure out the important information about this data, right? And you can do a histogram here. You can do like dot plots, but then with very few numbers, it's hard to put dots, you know? So we mostly deal with histograms when we're dealing with numerical data. It's like the neatest way to organize it. Once it's organized from least to greatest, right, then your goal is to calculate the 5-number summary. Right? In the middle, we're going to find the median. It's like the middle of all the values. So you literally go from last to right, and you go all the way until you find the middle. Right? If you have an extra term, right, and you're left with like 2 in the middle, you find the average to find the median. Right? You find the average between the 2 if it lands in the middle of 2 terms. Otherwise, it's literally the 1 number in the middle. But the median represents the 50th percentile, right? The cutoff. Like half of the data is to the left, half of the data is to the right. And then you start getting into percentiles, you start getting into like making sense of these numbers, right? The highest value is known as the maximum, and then you have the minimum. And then right in the middle of the smallest value in the median, you have your first quartile, your Q1, which is your 25th percent. And then in the middle of the 50% and the maximum, you have your third quartile, which is your 75%. Yeah? And this is me trunking all of that stuff, right, into just 5 numbers. But those are the most important 5 numbers. Those are the 5 numbers that you use when you're working with your box plot, right? This is your median. This is your Q3. This is your Q1, your minimum, your maximum. And then if you have any like outliers, you can calculate the outliers by doing IQR times 1.5. Right? This is going to give us our outliers. IQR being the interquartile range, which is the range of the interquartiles, right? This is the interquartile range. So Q3 minus Q1. Whatever number you end up having in your data, right? You subtract that number minus the first number, and you get a number here for your IQR. That's basically your spread for this information. Right? How far is your data spread out in the middle? Like the middle 50%, how much is it spread out? Versus like the full range is maximum minus minimum, right? Interquartile is in the middle. And then to find the IQR, once you subtract those, you multiply that number by 1.5, and that tells you how much away, right? If you add that 1.5 times IQR, it tells you if you have any outliers in the top, or if you subtract, right, the minus 1.5 times the IQR, it'll tell you if you have any outliers on the left. if like any points exist that are beyond or below the minimum and maximum ranges. Right. So when you're describing numbers like that, you describe. There's different ways of remembering this, right? When you do your descriptions, and we'll talk more about this later. But talk about socks. We're dealing with the shape. You're dealing with outliers. You're dealing with the center and the spread. Right? So in terms of shape, is it symmetrical? Is it skewed? Right? Skewed to the left, skewed to the right. I use my feet. I literally put my feet. I look at my toes and I'm like, all right, which one's skewed left? My left foot will have a big toe here. Right? I can't see it. And then all my little toes go down. So that's left skewed. My left foot is left skewed. My right foot is right skewed. Assuming that you have normal feet, right? And if your feet are not normal, then no offense, just learn other people's feet. But that's how I tell the difference between like the shape, right? Is this left skewed or is it right skewed? And that's when you're dealing with the shape, right? So one thing you describe is the shape of the distribution. Outliers is if you have anything that appears to be an outlier, as there's something that seems to be like pretty far away from the center, right? As long as you keep things vague, you can say like there appears to be an outlier at this number, unless they ask you to calculate the specific outlier, right? And then center, we're dealing with median or mean, which is the average, right? Those are the ways that you measure center. As a way to describe the most typical number or the most typical value, right? That's what we use for center. Like the average age in this room is probably like 18 years old, right? If you don't count the teachers in the room, right? And then we are clearly the outliers of the distribution. And talking about the center gives you a pretty good idea of what the general population looks like, right? And then for spread, you're dealing with range, IQR, or standard deviation. And we'll talk about that in a minute, right? That's really how you describe the spread of a distribution. But yeah, one of the FRQs will definitely be, given a distribution, can you describe it? And as long as you give all of those terms some context, right? You don't just say it's skewed, the center is this number, like don't list specifics, but like you talk about the age of the basketball players, whatever context they give you, if you talk about it in context, you'll get majority of your credit for sure. Questions? Okay. They're not going to ask you to find standard deviation like you calculate at the beginning of the school year, but they will, I mean, it is used a lot, right? So standard deviation, let's talk about what that means. Standard deviation, because this term gets used in every test, pretty much, right? You have sample standard deviation, you have population standard deviation, but standard deviation can be given this symbol, right? We got sigma, and we have this one right here. These are the most common symbols. This is when you're dealing with like the population versus your sample, right? Standard deviation is a measure of how far on average you are from the center, right? So how far on average a value is from the center or the mean, right? Like if the test average, if the average test score was a 50 on the exam for your class, right, and the standard deviation was 10 points, that tells me that on average, a student was between what two numbers? 40 and 60. Because you're 10 points away from the mean on average. Now, some people might be higher, some people might be lower, right? But this right here describes the spread of the distribution. It describes how far the values are spread out, right? The higher the standard deviation, the more things are spread out, right? The smaller the standard deviation, the tighter things get, right? The closer they get to like the mean versus the more they're going to be spread out from the mean. Yeah. So you use this term a lot, right? You use the standard deviation as a way to describe how much things vary, right? The variability, how much things change, right, compared to the average value. Doing okay? If you're dealing with, like with IQR, if you're dealing with box plots, right, we're going to be using median, and usually you have range and IQR. Those are the terms that you're going to be referring to when you're dealing with like box plots. When you're dealing with histograms, you're focusing mostly on the mean of a distribution and the standard deviation. It doesn't really matter how you represent stuff. It really comes down to like what is better visual, right? And as long as you can read both visuals, can you tell when something is skewed? Can you tell when something is symmetrical, right? Can you look at the shape? The shape is easier to look at than histograms, but you can still sort of tell, right? If things are evenly spread out from the mean, or if things are not so easily spread out, because this is the middle, right? This is 50% of the data, so half the data is concentrated here, and the other half is spread out further. So this would be like a right skewed distribution, versus your histogram would have like your curves, and looking at that kind of shape. So I'm comfortable describing the shape by looking at either a box plot or a histogram. When things are symmetrical, we use mean and standard deviation for the measure of center and spread. Right? When they're not symmetrical, so like when they're skewed, we use the median and IQR. And that's because if the data is really spread out and kind of skewed to the right, like if we're looking at the average income, right? Average income, you're going to incorporate over here your Zuckerbergs, your Teslas, your Bill Gates, your Amazon owners, like all the people over here that are going to clearly skew the data, right? You got like your billionaires and your trillionaires are going to skew the mean, right? So we use the median to describe the more common or more typical income level, right, that people make. Because the average is going to be pulled away by these outliers, right? So when you're looking at a histogram, if it is skewed right or skewed left, the center would be your median, and then your average will always be pulled further up. It'll always get pulled wherever the tail is at. If it's skewed to the left, the average will be below the median, right? If it's skewed to the right, then the average will be higher because it's going to get pulled by those other numbers. Like the average age in this room is not 18 years old if you incorporate the two teachers, right? Our two numbers are going to make your average, oh, the average kid here is 22 years old. But people are here on average aren't 22. So we don't use 22 years old, we use the median because it eliminates all those outliers. The median, when you're calculating it, right, you don't really care about youngest, oldest, you care about what's in the center, right? So we use the median and the interquartile range, the middle chunk of the information when you have outliers. And when you don't, it is more common to use mean and standard deviation because it's the center and it's the spread of everything because it's pretty balanced. Is that okay? Okay. Now I know there's a lot of here, but it's the foundation to where we're going and where we need to go. Is that okay? Okay. Any questions? Yeah. Mm-hmm. Yeah, so we use the sigma here when we're dealing with the population information. So in this room, we have a sample of all the statistics kids in this class, in Taft. So if we take the average of this room, it would be a sample, because we clearly don't have everybody's data. right? If we had everybody here today and we took the average, then the standard deviation would be the population, because we're now talking about everyone is included, right? And knowing the differences is important because that's what's going to help us determine what type of test. So that's a really good question, right? If you know all the information of everybody in the population, you're going to use this one and the mean, right? These are the two variables for center and spread when you have the population. So you literally calculate everyone's age and you find the spread of all the values that you have. For a sample, which is most likely to happen, you're going to use X bar and standard deviation, because it's easier to take a sample, find that average, as opposed to, hey, let's get everybody here today. People can't do that, right? Even like when you do, what is that survey that they do when they go to houses every 10 years? The census, even then, they can't get the whole population. It's impossible to get everyone involved or accounted for, right? Because they're traveling for their trips, or they're not home, or they work late, or the night. It's impossible, right? So we use in statistics a sample that is representative of the population, a non-biased sample to make our predictions, right? I can sample 50 people as opposed to 500,000 people, right? Instead of the population of 8 billion, why don't we just sample the state? And maybe if that state is indicative of the entire population, we can use that sample to talk about everyone else, right? So we use a sample to make predictions on everyone, as long as it's a good sample, right? Which requires it to be non-biased. It requires it to be a random sample. And then you start getting into all the other conditions for your test, right? Is it approximately normal? Is the sample large enough? Is it indicative of the population? I can't just sample females and say, how much do you like statistics? Because then we're excluding the male vote, right? It's got to be indicative of both. And it can't just be the athletes. It's got to be the athletes, the band students, all the different populations, so that it is indicative. The sample has to represent the population. It's like a small version of the population. That's what we would consider a good sample. And with smaller numbers, you can calculate the information easier, right, than calculating it for hundreds of thousands of people. Although we have computers that can do that, right? Does that answer your question a little bit? Perfect. Okay. So, are we okay with when to use median and IQR as opposed to mean and standard deviation? Right? Spread versus not spread. The shape, looking at your feet. Are we okay with standard deviation, the meaning of standard deviation? How far on average is a value from the center? And it's on average.
Will give us like the standard.
Yeah, you'll be given standard deviation, and your goal is to interpret it.
Okay.
Right? Can you describe the meaning of that number?
For like an effort, if we're trying to find the sign of difference summary and describe it, is that like a situation where we would find all the numbers? Like
They usually would give you in an FRQ, if anything, like a box plot. And then you're like, well, here I can find the median, right? I can find the median value here, because that's the middle. I can find the IQR, because I can subtract Q3 versus Q1 and compare this Q3 to this Q1. So I can compare the data. That's how you would see it, but not by numbers where you're going to have to organize all of them and take forever. But from here, you could describe the differences between the two, right? Like, and we can talk about examples and stuff. Okay, let's see. So we talked about this pretty much already. When you're comparing, right, information, you do want to compare the shape, the center, outliers, and the spread. You want to compare all four things of these two, right? And you want to use comparative language like higher, more than this one, or is it about the same as this one, right? It's kind of like how in English, you can't just like list the things of one and list the things of the other. It's compare and contrast, right? So you got to use language that does that. By saying that males are on average taller than females because the median height is 40 versus 30 something inches, right? You're using numbers, you're using context, and you're saying the word on average. You're not saying they're always higher than the girls or they're always taller, because that's more definitive language, right? Some values are clearly low or some values are clearly higher. So we use language that is like on average, right? Very vague. And at the same time, we use things like that creates context while comparing them. Versus the height of males on average is 60 inches and the height of a female on average is 50 inches. The center or the spread of this, the spread of that, right? You want to use language that compares them while using specific numbers and stuff at the same time. Yeah. We're not going to go necessarily to that question because I do want to get to our normal curve a little bit, unless we can circle back and do some examples specifically. But I do want to talk about like the empirical rule, and when you're dealing with normal distribution or approximately normal distribution, right? The empirical rule. Do we know that rule? Dealing with 3 standard deviations, right? So when you're from the center, 95. So when you're 1 standard deviation away from the mean, when the data is symmetrically distributed, right? And approximately symmetrical is what we're going to say, right? When it's approximately symmetrical distributed, you're going to have 68% of the population within 1 standard deviation, which is a good chunk of it, right? More than half of your data will be within 1 standard deviation. So if we go back to that example of how the average test score was a 50 and the spread was 10, we're saying that 68% of the people in the class were between a 40 and a 60, because that's like the plus 10 and the minus 10. 68% of them, when the data is normally distributed, it's like that. Now, if the class cheats, then it's going to be skewed. And you can't really use these numbers when the data is skewed because it won't cover the same percentages, right? So we use the empirical rule to talk about things when they're spread out because they're going to be evenly centered from the center, from the median or the mean, right? When you're dealing with 2 standard deviations, it's 95%. 95% of the data will be within 2 standard deviations. So on that exam that I would give you the example 50 and 10, right? 10 points. Now you're dealing with 20 above, so a 70 and a 30. So now 95% of the people were somewhere between a 30 on the test and a 70 on the test. And then the 99.5 is the last one. 99.5 would be your 3 standard deviations. Which is why in your Z table and your T table, you don't go much higher than like, yeah, you can't get to the 100th percentile and stuff, right? So you can get pretty much everybody. Will there randomly be maybe your one person that got 100 on the test when everyone bombed it? So there's a chance that happens, right? You have outliers, right? But the majority of the population will follow this distribution if it's normally distributed. So like here I have an example of how to use the empirical rule to make your calculations. And it's talking about like alligators, right? They're only native to the United States and China. Now, the adult males on average will be 11.2 feet, and the standard deviation is 2.06 feet. You can use that information to create a general curve of these populations to calculate your stuff, right? So you would put 11.2 in the middle, and then you're literally adding 2.06, 2.06, 2.06 to fill out your curve for those heights. This is what, 13.26, and then if you add 2.6 more, I should have used prettier numbers, right? But this is actual data. I didn't want to mess with stats. When you add 2.06, now you have 15.32. When you add 2.06, 17.38. I appreciate the help here because my brain is not thinking. And if you subtract 2.06, and if you have a calculator, this will be a lot faster. 9.14, okay, and then minus 2.06, 7.08, and then minus that 5.02. Look at me. Oh, watch out. So now this is the majority of your alligators. Will you have alligators below 5 feet and above 17? You bet, right? But we can calculate here the percent of the alligators that are within certain ranges, right? And here are some scenarios, right? And these are kind of like the multiple choice kind of questions you can get. This wouldn't be an FRQ question. An FRQ question, you would use the Z table and you would calculate the Z score, right? And I'll tell you when to use that in a minute. But these are like general scenarios, right? What proportion of the alligators are between 9.14 and 13.26? So that's between this value and this value. Well, that's one standard deviation, right? That's one above and one below. That's what percent? 68%. So you can do that without any calculator, without any calculations, because you can see that the inside of those two is going to be 68%. And you can go through that list, right? How many are between 5.02 and 1738? That's your 3 standard deviation. That's your 99.5%, right? Between 7.08 and 1532, that's 2 standard deviations. That's your 95. And then you have stuff in between, right, that you can also calculate. So it does help to also cut this in half. To cut your data in half, you can then look at, well, what's 68% divided by 2? That means that that's 34 above, and that's 34% below, right? You can look at the differences, and you can calculate those little percentages in between for the above and for the below, so that you can find the other ones, right? Like, what percent is between 5.02 and 7.08? And you can find those little specifics. Were you okay with that? And you would literally just cut the difference, right? Find the difference between 95 and 68, and then divide it by 2 so you can separate into the percents. And then in the end, they should all add up to pretty close to 100% or 99.5%. Yeah? Do we have these percents already? Some of you that are good with decimals? Yeah? No? So you would... 13.5% here. Yeah. Above and below. And you just did 95 minus 68 divided by 2.
Yeah.
So that you can cut those in half. And then when you add these, you can basically divide the 99.5 in half, and then you subtract from whatever's there. And it's just like a little small percentage. 3, 4, 7, 47.5, and half of 99. You know, it's a small number. But like that's how you would end up calculating other specific stuff. What happens if they ask you a question like what percent of the alligators are less than 12 feet? Where does 12 feet land? Between the mean and 1 standard deviation. When it's exactly a specific value, we start getting into z-scores. Because the z-score allows you to compare the observed value minus the mean over the standard deviation. And by this one, just to be congruent, I'm going to use, these are not samples, these are actual values. I'm going to use those two. The mean and the standard deviation. When you subtract your observed, the value of interest from the mean and divided by standard deviation, you can find the exact location, the exact z-score of that value, right? And that z-score can be then computed from your z-table. You can find that percent for the exact location, right? But when it's general locations, you can find those without z-scores. Or you can do all of them with z-scores, right? Anyone want to interpret what a z-score is?
How much of the distribution is included? So like if you have this less than 12 feet, your z-score would find the percentage of allocations that are less than 12 feet.
Yeah, it can help you find the percentile, right? It helps you find the number below that the location you're interested in. But in general, if you have a negative, positive, whatever z-score, a z-score measures the spread as well. So just like standard deviation, if we go back to our definition, how far on average a value is from the mean, right? You can also figure out that a z-score is how many standard deviations you are from the mean, right? So one standard deviation, right, it tells us how far a value, that one value is from the center. A z-score is how many standard deviations you are from the mean, right? So z represents how many standard deviations you are from the mean. And you can convert that, as you said, to percents. You can convert that to other stuff, right? But a z-score allows you to compare different distributions with each other, right? So like if I wanted to compare, say, the United States alligators versus the China alligators, they're going to have different means and different standard deviations. I can't just say, oh, these are longer than those other ones. They're bigger. These are shorter by just comparing the averages, right? You would have to use the z-score to compare those to each other, right? That's when you talk about normalizing the data so that you can then talk about it. You can't say that your average, say that your average in statistics is a 90, right? And then someone's average at O'Connor is a 91. Are they smarter than you? No, because those are two different campuses, two different populations. Even if the number is higher, what if that data is just on average higher? And a 91 over there is low. And a 90 here is like the highest grade possible, right? So when you're comparing percentages or averages to each other and the populations don't come from the same place, we use the z-score to compare those. The z-score for someone here in Taft is like a 3.2 and someone over there is a 2.1. Now you can say this person performed higher relative to their people than the other person relative to theirs. That's how we compare averages. You can't just say, oh, well, they're on average taller. But to who, right? The z-score allows us to compare two different distributions because it measures how far this value is from their respective mean or their respective center, right? And then we can, look at examples of stuff and stuff like that. But does this sort of help a little bit? Z-score, what it means. This is a very powerful tool. When you know the population information. And this is really the only chapter that you know all the details, because as you move forward, you do experiments and you know samples. You don't really know the mean and the standard deviation. You know some of that. So we'll get into other tests later. But for now, if you glimpse through some of these, are we comfortable with some of this? Look at like this question, right? What percentage of the adult alligators have lengths between 12 and 14? Are those values in our empirical rule? No. So I would have to calculate the z-score for both to find the percentages that belongs to each and then subtract the two, because those numbers can't be calculated for here. We would. Yeah, so like for this one right here, right? Since we're here, let's just wrap it up with this question. We would find the z-score for 12. So we would say 12 is my observed minus the average, which is 11.2 over the standard deviations, right? That would give me a z-score. That would then like tell me this percent. We'll call it z1. Yeah? No, I'm not showing people. Sorry. So when I calculate the z-score, you take your observed value This is the data point minus the mean that they gave us, 11.2, and they divided by the standard deviation. That gives me a z-score, which will then also in the table give me a percent, right? I would then calculate for 14 feet. Calculate that z-score. So you would have z equals 14, the observed, minus the mean, over the standard deviation. And then this z-score would be higher because it's 14, right? Which would have a higher percentage. This is my z2. How would I find the value, how many percents is between the two? Subtract the percentages. That gives you the part that overlaps. And then you would use the percents from the table that you would use. That's information to be given, right? Subtract the two and you can find the exact percent between the two of those. Right? And then you can figure out, well, what percent of the alligators are not between 12 and 14. And then you just subtract that number from 1 because it's the complement, right? Everything will always average or add up to 100%. So if you find the in between, you can subtract it from 1 to find the not. Right? So these are the kind of questions that you would see on multiple choice. Right? Calculations, things that you have to do stuff with. You will have to calculate a little bit when you get to the FRQs, but those are more like you got to write out your null hypothesis, your alternative, and I'll show you all the format later for that. So that you have a general outline for all tests, right? And you'll do one calculation, but mostly it's writing. You'll spend 10 to 12 minutes explaining this is the null hypothesis, this is the alternative, this is the mean, or the mean and standard deviation is given, and it's more about explaining the math. Do you reject the null, find the probabilities, all of the stuff. We'll get to that.
Okay. So is this going to be about the calculator and then you don't really have the response mark, or is it going to be all calculated and the response?
It's two parts. You'll get 90 minutes for the free response for 6 questions, which is the first 5 questions, and we'll get to those specifics. Those first 5 questions are about 10 to 12 minutes. Those are short FRQs. Questions like this one would be an FRQ question. Compare the distribution between the dogs and cats or something, right? That would be a question that you would be able to answer, or you're given a histogram, or right? And then multiple choice, you'll see more of this kind of stuff. And then I got to look at more up to date of what they have for calculator versus non-calculator. But usually, yeah, if you need it, they'll give it to you. Like it should. They're not going to have you calculate a z-score by hand and divide 2.07 by whatever. No, we're not going to do that. They're not going to do that. They are more interested in, do you know how to explain the math behind it? Yeah. So if you can see here, right, here's an example of how you're comparing 2 populations. The Miami-Dade Zoological Park and Gardens is the largest zoo in Florida and has an exhibit host a 14-foot alligator. What percent of the adult male alligators are smaller or larger? Right, you would have to calculate the percent below the graph, right? Your z-table would be everything below. The larger would be 1 minus whatever percent you get. And if you forget, your z-table has a picture there that's like graphed, you know. And then there's like the working your way backwards from the table too, in terms of an example with z-scores. Like, could you calculate the top 10 percentile? Can you calculate the IQR? Or you work your way back, right? Because from a z-score, I'll put it over here. If you have the z-score, you're going to compare the observed value minus the mean over the standard deviation. This z-score will then help me find, I locate the z value, and it'll help you find everything below it, right? This is when you're given the observation, you're given x. Then they also tell you, like, well, what about the top 10 percentile? We're going to have to work backwards, right? We're going to start by finding the percent. What z-score would give me a 90th percentile? and you can find the closest value you can to the z on the table. Find whatever value you can get closest to 0.90, right? That z-score, you're going to plug it into your equation because you now know that from the table. And you're going to find what x value, if I compare it to my data, what x value would give me that percentile. And you would just use a basic algebra, right? You multiply both by 2.06, you add 11.2, and you can find the exact value that results in that percentage. So that's how you would work backwards from the z-table. Whew. How are we doing? There's a lot, right? Okay, so standard deviation, z-scores, we're looking at mean, median, IQR, range. There's just a lot, right? And that's like the first big chunk of it. And if you have an understanding of the meaning of those words and when to use them, the rest will soothe a lot and it'll become a lot easier. Because everything is in context with the understanding of what a z-score means, right? Do I know what that represents? And I have examples. We can go over more examples like next week, right? And I can talk about these, the application of it and comparing the z-scores and all that stuff. But hopefully this gives us a pretty good understanding of the intro of things. Yeah? Okay. I'll be posting this online. It's a 46-minute video.